laws of resistances. You see, for the resistance, we studied one formula, that's R rho L upon E. Rho here is a specific resistance. We have to focus first of all on the length and area. Suppose you have a rectangular box and you want to find the volume of that box. Then it's not mandatory that you choose length to this side or this side, that's your choice. But here in this relation, it is mandatory. Length cannot be taken as any part of this box. For choosing the length, we have to be particular. We have to see what is the direction of the current. If the current is flowing this way, then length would be taken along the current and A perpendicular to the direction of current. So let's emphasize this thing, that whenever we measure the length, we have to be particular regarding the direction of current. Let's say that length is always along the current and cross-sectional area is always taken perpendicular to it. One example I have given over here. You see this rectangular box. I'll give you one example. Suppose two faces have been taken, and the sides, as I have mentioned here, A, B, and C. This side, let's say, is A, this is B, and this one is C. All the three sides have been shown over here, and you want to find the resistance between these two faces, this left face and the right face. When we say that we are going to find the resistance between left and right face, it means the current is flowing from left to right. And that's why we are going to consider the length as A. So in place of length, you are going to write A. And area perpendicular to this current flow, that is going to be B into C. This surface will be like this. And for finding the area, you have to multiply this C by B. It will be rectangular shape, and that's why we are going to multiply length with the width. So for finding the area, you are going to write B into C. This becomes the resistance between the two faces, extreme left and extreme right. One method I have told you, one example. Then I would consider cylindrical conductors. Let's suppose it is solid one, solid cylinder, this one. Here, if it is completely filled, then only you would call it solid cylinder. In that case, length L and cross-sectional area. Then, if you consider hollow cylinder means you are having inner and outer radii for the given cylinder, might be R1, R2, and the solid portion is between them, means R2 minus R1. This is going to be the portion filled with the material. So effective area here would be pi R2 square minus R1 square. In place of area, you are going to write this formula. Then obviously the resistance will be given by rho L upon, in place of A, you are going to have this value, and the formula becomes this one. Now we will consider what is the effect of stretching the wire. You see, wire, 99.99% wire means it always conveys the message that it is having cylindrical shape. So either you talk in terms of cylinder or wire, both carry the same meaning. If a wire is stretched like this, you are not adding material, you are not reducing material. Of course, you are adding energy, but mass is not going to change over here. Mass will be constant. Once you say mass is constant, and by stretching or by compressing, density will not be considered as variable. So, density also remains constant. You say mass is constant, density is also constant. Obviously, the inference is that volume would be constant. Volume for a cylinder is area into length. Volume both the times means initially and finally, both the time volume should be constant. So, it becomes A1 L1 A2 L2. Then it means L1 upon L2. This is A2 upon A1. You might say the inverse of square of their radii. Ratio of length is the inverse ratio of square of their radii. Formula rho L upon A. And you got one special interesting condition over here, that volume is not going to change during stretching. So, let's introduce somehow volume in this relation so that we might ignore it being constant. We'll simply multiply it by L. Now, what becomes is rho L square upon V. Rho is characteristic of material, and you have imposed one condition that volume will not change. So, what remains variable now is only length. Obviously, you get one important relation, R proportional to L square. So, if initial and final length are known to you in the process of stretching, you might say this is, and here you got the relation with the square of the radius. So, it's going to be R2 upon R1 power 4. Resistances ratio, inverse of radii is fourth power. Both are equal. But let's summarize the whole thing in a very tricky style, that if length is going to be increased by 2%, square of 2, that's 4. If the length is increased to 2%, obviously the resistance will increase to 4%. So, you have to remember, once length increases n%, small n, then radius will also change. That will be related in other parts. Simply you remember in terms of length only. If length is increased by n%, resistance will increase by 2n%. But here again, it will not be sufficient to memorize this much only, because here you have applied the condition of stretching, and once you stretch, you could say this thing is okay. The length increases 3%, you would say resistance has increased to 6%. This increase was by the process of stretching. It will be applicable only up to 10%, not beyond that. If it is compressed, then also the same thing, you could talk in terms of radius. But above all, this relation also suggests one very important and peculiar relation. Rho is already constant, R is proportional to L. This is very important relation. But is it independent? No, not at all. It is dependent on one particular condition. We have considered this as constant. What does it mean? This is wire. It is having some length. It is having some area. You have to increase the length without changing the area, means you have to maintain the area constant. And this could be possible only by adding another one, similar one. Now the length has been doubled, but the area is maintained constant. Here in this situation, this law is going to be applicable. Similarly, This is also applicable with the condition that length is constant. In certain books, you'll find the laws of resistances like this. These two laws are also known as laws of resistance, whereas for stretching, we got this relation, and at the same time, this also. Both the relations for stretching and compressing. So, all the conditions we have covered.